Welcome to Prospective Doctors MCAT Podcast, brought to you by Med School Coach. Each week, Sam breaks down the highest yield MCAT topics so you can score as high as possible on test day.
Hello and welcome to Prospective Doctors MCAT Basics with your host Sam Smith. The goal of this podcast is to cover the highest yield topics on the MCAT and provide you with some sort of insight into the questions that the MCAT really likes to ask. This podcast covers the three most common types of isomers that you'll see on the MCAT. That's going to be structural isomers, stereoisomers, and geometric isomers, which geometric isomers are technically stereoisomers as well, but they're important, so I'm kind of breaking them off and talking about them on their own. And with each of these different types of isomers, I'll first give you a definition, talk about a common example, and then I'll talk about some of the major applications that you're most likely to see on the MCAT, like for instance, how geometric isomers are related to elimination reactions. And this material is going to show up on one of the four subsections of the MCAT, which is going to be the Phys-Chem section, although you might see a little bit maybe in Biochem. I guess that's possible. Anyways, thanks for listening to this podcast, and I hope that it helps in your studies. All right, so as I was saying in the intro, I'm going to talk about three different kinds of isomers. I'm going to start here with structural isomers. And structural isomers are also called constitutional isomers, and they are molecules which have the same molecular formula, but have different connectivities or different atomic organizations. And so to me, these are kind of like the classic isomer, right? I give you some molecular formula, say it's pentane, C5H12, and now I ask you to draw as many structures as you can with that same molecular formula. Well, those are all going to be structural or constitutional isomers. And pentane itself has three different structural isomers. The first is N-pentane or normal pentane, and that's just a single straight chain of 5 carbons. And then you have isopentane, which is also 2-methylbutane, which is this 4-carbon straight chain. And then you have a single carbon chain coming off of the second carbon on that 4-carbon chain. And then you have neopentane or dimethylpropane. And so this is just literally imagine a central carbon, and then you have 4 carbons sticking out of it. So there's 3 structural isomers. They have the same molecular formula, but different connectivities. And I just want to reiterate here, I think I talked about this back in the bonus episode I did on organic chemistry, that I wouldn't put a ton of effort into actually knowing how to produce the names for these different molecules. Be able to kind of recognize and be able to put together names, because you're going to be either given right the name or the structure of some compound. You're going to be able to then need to recognize the structure or recognize the name and kind of match it, right? Because you're not going to be typing in a name. You're not just producing a name from nowhere. You got to look at a name, be able to deconstruct, okay, I know what di means, I know what methyl means, I know what propane means. Okay, this is what this structure must look like. You're not going to have to produce that from nowhere. So just keep that in mind as you're studying. And in terms of a formula for the number of structural isomers for some certain compound, there is none. There's no easy formula available where you can plug in, the number of carbons or hydrogens or whatever, and then figure out how many structural isomers you're going to have. If you get a problem like that, which I don't think I ever saw anything quite like that on the MCAT, you'd have to actually sketch out each structural isomer and then determine the number from there. So just keep that in mind. You can't use like 2 to the n, which is a formula I'll get to later that you actually may use on the MCAT, but there's no easy formula for determining the number of structural isomers. Beyond understanding the general definition of a structural isomer, there's not a whole lot of applicability on the MCAT. One thing that I would note is that these different isomers will actually have different physical properties. So for instance, the boiling points of N-pentane, isopentane, and neopentane are all pretty different. For N-pentane, it has a boiling point of 97 degrees Fahrenheit, whereas isopentane has a boiling point of 82 degrees Fahrenheit, and neopentane has a boiling point of 49 degrees Fahrenheit. So you can see based upon their structure, they all have these different boiling points. And again, I think I talked about this in an earlier podcast, but that just has to do with the fact that there are more or less intramolecular interactions, and molecules can kind of pack up tighter, have more interaction, and therefore have a higher boiling point when they're in that long chain N-pentane form. based upon this principle of molecules being able to either pack tighter or not be able to pack as tight because of their three-dimensional shape. These molecules all have different densities as well. N-pentane is the highest, whereas neopentane is the lowest. So I think that's one interesting application of these structural isomers, is that they all have different physical properties based upon their three-dimensional structure, based upon how tightly they can pack, based upon their intramolecular interactions. The next type of isomer I want to talk about here is called a geometric isomer. And sometimes geometric isomers are called configurational isomers. I haven't really heard that very much, but I've heard them called like cis-trans isomers. Sometimes you might see that a little bit more. But these are two or more compounds which differ from each other in the arrangement of groups with respect to a double bond, ring, or other rigid structure. And I'm mostly seeing this in terms of a double bond, but just keep in mind that any type of ring or rigid structure can also have different geometric isomers. They can have a trans form and a cis form. So I'll get into what cis and trans are. Cis and trans are simply the names that are assigned to geometric isomers. So if you remember back to organic chemistry, cis, or I guess this was probably in general chemistry maybe, but cis is the isomer in which the highest priority groups on either side of the double bond are on the same side of that double bond. So say, for instance, you have two high priority groups, you've identified them on both sides of the double bond, and they're both pointed up, well then that's going to be the cis isomer. The trans isomer, on the other hand, is when the highest priority groups on each side of the double bond are on opposite sides of that molecule. So, again, you've found out which are the highest priority groups on both sides of the double bond. And the trans isomer is where you have one of those high priority groups facing up, the other group facing down. It's trans. The way I remember this is that trans has a T, opposite has a T, cis and same do not have T's. So I just remember trans, there's a T, same as opposite. That's kind of how I remember that. And you also see naming in another way. You'll see the EZ naming system where E, which stands for entgegen, which is a German word meaning opposite, is the trans isomer, whereas Z, which stands for zusammen, which is the German word for together, is the cis isomer. So you can remember E is the trans isomer, Z is the cis isomer. Those mean the exact same thing. Now I remember this because I took German in high school, so I kind of know zusammen means together, so I just remember that. But you can think about how a German person would say same with an accent. So they would say it like same, this is the same isomer, which is a horrible German accent, but you get the point. So Z goes with same, and therefore Z, same side, which also is cis. And real quickly too, I wanted to mention the priority rules. So you notice how I may have said that when the highest priority groups are on the same side, that is the cis isomer. Well, how do I know which groups are the more high priority? Well, all you got to do is you got to look at the atomic number for the atoms that are involved. And the rule is that the higher the atomic number, the higher priority that group receives. So typically you're going to have two carbons and they're going to be double bound together, and then each of those carbons will have two substituent groups coming out of them. All you got to do is you got to compare the atomic numbers of the substituent groups. Maybe one's a carbon directly bound to that double bound carbon, and then the other group is like a hydrogen. Well, carbon has a higher atomic number, so that is automatically the higher priority atom. I recommend going and practicing this. It gets a little tricky, especially if there's a tie and it's basically the same on both sides. Then you got to go to the next atom out and check and see, okay, what's the atomic number of this atom, and so forth until you determine a difference between the two substituent groups. This may sound a bit confusing just hearing it in words. So if this isn't making any sense to you, or you're like, I've never heard of this before, I would go practice and go assign priorities to different isomers and see if you can determine whether this isomer is either the E form or the Z form, or cis or trans or whatever. Go practice. If not, and you're like, oh, okay, yeah, assigning priority, higher atomic number, that rings a bell, then you're good. but you will probably see this come up on the MCAT. So again, geometric isomers are two or more compounds that differ from each other in the arrangement of groups with respect to a double bond, a ring, or some other rigid structure. So I just wanted to quickly mention that you can have cis or trans isomers when you have a ring. So let's say you have like a 6-carbon ring, your classic, what is that, hexane? Oh no, cyclohexane. So say you have cyclohexane and you have two substituent groups coming out of cyclohexane at like two different points in the ring. So if you imagine this hexane ring as being this flat 2D shape, well then you can either have these substituent groups pointing out at you or into the page. And so if you have those groups facing both out at you or both into the page, that's going to be the cis isomer. And if you have one of those substituent groups pointing at you, one of them pointing away from you, that's the trans isomer. So it's just important to keep in mind that you can have these isomers with ring structures as well. I haven't really seen that on the MCAT, but you never know. They might throw something at you, and because it's this 2D cyclohexane ring with just these substituent groups, you're thinking, no, there's no stereoisomers here. But there are. There is actually a geometric stereoisomer, so just keep that in mind. So the two applications here I want to talk about are first in terms of the physical properties of these geometric isomers, and then talk about their application in elimination reactions or E reactions. Like with structural isomers, the physical properties of geometric isomers depend on whether you're looking at the cis isomer or the trans isomer. And of course, this is very dependent upon what the substituent groups are. Are you looking at one polar and one nonpolar substituent group on both sides, or are you looking at two nonpolar substituent groups? Take, for example, pent-2-ene, which is a very nonpolar compound that is capable of having both cis and a trans isomer. And because these substituent groups are very nonpolar, the cis and the trans isomers don't really differ that much. For instance, the boiling point of the cis isomer is 37 degrees Celsius, whereas the boiling point for the trans isomer is 36 degrees Celsius. So there's only a 1 degree Celsius difference between those two isomers because the substituent groups are very nonpolar. On the other hand, if you have a compound like 1,2-difluoroethene, which has a polar fluorine atom on each side of the double bond, then you're going to have much wider variance in these physical properties between isomers. So for instance, the cis isomer of 1,2-difluoroethylene has a boiling point of minus 20 degrees Celsius, whereas the trans isomer has a boiling point of minus 40 degrees Celsius. So there's a much bigger difference in boiling points between these two molecules because of this polar substituent group that is in the molecule. So my summary here is that the physical properties of geometric isomers are different in general, but their degree of difference depends upon the substituent groups. As I mentioned, the second application I want to talk about is in terms of elimination reactions. So the two most common organic reactions on the MCAT, in my experience, are SN1 and SN2, and E1 and E2. And so, I guess in general, OChem reactions are fairly low. Like I've seen, maybe 1 or 2 questions at most on a single exam. But those are still questions you want to get right. So, in general, an elimination reaction is a reaction in which you remove or eliminate 2 substituent groups from a molecule to form a carbon-to-carbon double bond. And obviously, when you form a double bond, there can be different arrangements of the substituent groups to either form the cis product or to form the trans product. And in general, you need to know that the elimination reaction will tend to favor the trans isomer. And that's because the trans isomer tends to be more stable and there's less unfavorable steric interaction between substituent groups, especially if there's some really polar molecule, right, that is between this double bond. So go back to the example I was talking about before of the 1,2-difluoroethene. Well, those 2 fluorine groups don't want to be near each other. So when you put them in that cis conformation, they're going to be like, let me get the hell away from this other fluorine. And so they like to be in that trans form, right? It's just more comfortable. It's more stable. And if you think back to OChem, you'll remember that the stability of the product of elimination determines what's going to be the major product, right? Because you can form a double bond on like the end of a molecule, you can form it in the middle, and it so happens that forming double bonds in the middle of molecules is better than the ends. And there's like one main rule that you got to remember in terms of product stability, and AKA what's going to be the major product of a reaction for elimination. And that's going to be that the more substituted an alkene is going to be more stable alkene. So, just kind of go by that rule. Remember that the trans isomer is more stable. Remember that the more substituted alkene is more stable, which is why you don't want to form a product that has the double bond on like the very tip end of that molecule.
Thanks for checking out the Prospective Doctor MCAT Basics podcast. Sam's doing a killer job taking you through the most important MCAT topics, but what if you need a little extra help? How does a 5, 10, or even 15-point increase in your score sound? Imagine how your chances at admission could increase. Med School Coach's MCAT tutoring can get you there. With the most rigorous selection process of any tutoring company, we see amazing results. We deconstruct each student, find a plan that is going to work, and help execute it. That's why our students add an average 12 points to their score. Completely physician-run and operated, and focusing on nothing but medicine. It's no wonder over 10,000 past students have trusted Med School Coach to get them through the MCAT and into medical school. Check out medschoolcoach.com today and mention code PODCAST for 5% off.
All right, I saved the best for last, which are stereoisomers. And this is probably the most important for the MCAT out of this whole podcast. So there's 3 different kinds of stereoisomers I'm going to talk about. I'm going to talk about enantiomers. I'm going to talk about diastereomers. No one knows how to say that word, diastereomers. We'll get into that. And then conformational isomers. All right, so in general, stereoisomers are isomers that have the same atomic connectivity, but differ in the spatial arrangement of atoms. So as I said a little bit earlier, geometric isomers or cis-trans isomers are technically stereoisomers. I like to pull them out because they're really important, but they are stereoisomers. However, when you typically think about a stereoisomer, you usually think about enantiomers and diastereomers. So let's get started with first talking about enantiomers. So these are stereoisomers that are non-superimposable mirror images of one another. The classic example here is your hands. So if you take your hands and you look at both of them, put them out in front of you, and you can see that they are mirror images, right? If you were to draw a plain line between both of them, one is just the mirror image of the other. However, if you took your right hand and now tried to lay it on top of your left hand, and what you have to do is you'd have to turn it palms up to make it fit. Well, now you try to do that, it's not the same object, right? Your right hand is not your left hand. They're non-superimposable mirror images. A more molecular example is D-glucose versus L-glucose. And if you look at a straight chain drawing of glucose, specifically of D-glucose versus L-glucose, you can see they only differ in the configuration at one carbon atom, which is like the carbon atom typically at the very bottom of the chain, depending on how you draw the chain. But again, these two molecules are non-superimposable mirror images of one another. On the other hand, diastereomers are stereoisomers that are not enantiomers. In other words, they are isomers that have the same atomic connectivity, but differ in their spatial arrangement of atoms, but are not non-superimposable mirror images of one another. And one common example of a diastereomer is what's known as an epimer. And this is a type of isomer in which the isomers differ in the configuration only at one stereogenetic center, and all of the other stereocenters in the molecule are the same. And this is something like glucose compared to galactose, which again is easy to see if you're looking at the straight chain representation of glucose versus galactose. So again, diastereomers are simply stereoisomers that aren't enantiomers. That is, I can draw their mirror image, and then I can actually impose that mirror image back on the original molecule, and it's the same molecule. All right, so the last type of stereoisomer I want to talk about are called conformational isomers. And these are a little bit weirder than the others. But stereoisomers are produced by rotating about some single bond. And what you're doing is you're actually rotating a group of atoms that are connected to a stereocenter. And a stereocenter is an atom that has at least 3 different attachments that is able to form a stereocenter. So an example of a stereocenter would be like a carbon that's attached to a fluorine, hydrogen, another carbon, and a chlorine. That's obviously 4 different things, but if there was a double bond involved, this carbon could be attached to 3 different things and still be a stereoisomer. So I guess the rule should be that a stereocenter is some type of atom that's connected to either 4 different types of atoms or connected to 3 different things with a double bond. And so conformational isomers are typically shown with a Newman projection. You might remember like butane, which I think is one of the classic examples, drawn in a Newman projection. And as you rotate one of those substituent groups around, you get these different conformations and therefore different conformational isomers. And there's a few different conformations that you might want to know. The first is the eclipsed conformation. The second is the gauche conformation. And the third is the anti-conformation. In butane, the eclipsed conformation is when you have this methyl group, the CH3 group, that is in line with the other CH3 group on the opposite side of the molecule. The gauche is when you rotate that front substituent group by 60 degrees. So you have one methyl group kind of cockeyed to the other at about 60 degrees. And then the anti-conformation is when you have the methyl groups on opposite ends of the molecule, like one's pointing up, one's pointing down on opposite sides. And that is typically the lowest energy conformation of butane. And that's where butane tends to like to hang out because it's in that lowest energy state. So just to summarize those, enantiomers are stereoisomers that are non-superimposable mirror images. And then you have distereomers, which are stereoisomers that are not enantiomers. Then you have conformational isomers, which are stereoisomers produced when you rotate a molecule around some single bond. All right, so I want to discuss a few important applications of stereoisomers that you might see on the MCAT. The first is a few terms related to stereoisomers you might see. The second is in identifying stereocenters. The third is in R and S naming, as well as relative versus absolute isomers. And then the last is in SN2 reactions. And then I'll add in a little bit about allulose versus sucralose versus glucose, which is just a non-MCAT interesting nutrition-related thing. So there's a few terms that you should know in reference to stereoisomers. The first is optically active. So what it means for a substance to be optically active is that it can actually rotate plane polarized light. And what type of molecules can do this? Well, chiral molecules can rotate plane polarized light. And now, of course, you're saying, okay, what is the definition of a chiral molecule? Well, a chiral molecule is simply a molecule that can have an enantiomer, i.e., it's a molecule that has a non-superimposable mirror image. So to quickly summarize that, in order for a compound to be optically active, it must be chiral and it must be an enantiomer. Another term you might see come up is mesocompound. And a mesocompound is a molecule that has multiple stereocenters that is superimposable on its mirror images, i.e., it is not non-superimposable. In other words, it's a molecule that has multiple stereocenters, so it appears to be optically active, but it's actually not. And why is it not? Well, it's because a mesocompound has an internal plane of symmetry. In other words, you can look at this mesocompound and you can draw a straight line through the molecule somewhere in it, and it will look exactly the same on each side of this line. So don't get fooled by a mesocompound, say you're given one. Don't be fooled into thinking that it is optically active because it's not. Instead, it's a mesocompound. The second application is in knowing how to identify stereocenters. And as I said earlier, a stereocenter is an atom that has at least 3 different attachments and is able to form a stereoisomer. Typically, this is going to be an atom connected to 4 different things or an atom connected to 3 different things with a double bond. And so you need to be able to look at this big, massive molecule and be able to pick out the stereocenters in the molecule and, either count them up. I've seen questions that say, how many stereocenters are in this molecule? And then it just gives you a molecule. So know how to do that. And my one piece of advice here would be to remember that hydrogens are typically not shown on molecular drawings. And so it's easy to forget to include a hydrogen. Like you might see an atom and you're like, oh, it's only connected to 3 different things. But then you realize, oh, hydrogens aren't drawn in on this drawing. So it actually is connected to 4 different things, and it is a stereocenter. So I recommend just practicing those types of questions if you are struggling with it. Another important application in terms of the stereocenters is calculating the number of stereoisomers a certain molecule can have. So again, let's say the MCAT shows you a compound, and then it says, for this compound, say drug X, how many stereoisomers are possible? Well, all you got to remember is that the number of possible stereoisomers is equal to 2 to the power of n, where n is the number of stereocenters. In other words, the number of stereoisomers you can have grows exponentially with the number of stereocenters that you have. The third application is in RS isomer naming, as well as relative versus absolute isomers. So there's a naming system for the stereoisomers, and that is naming them either R or S. And there's some Latin name, I don't really know how to pronounce it, so I'm not going to. But the rules for this naming system are very similar to the cis-trans naming. Essentially, you're going to assign priority to each of the groups that are attached to your stereocenter, and then you're going to rotate this molecule that you're looking at so that the lowest priority substituent is facing backwards. And then you're going to take the 3 substituents that are facing you, and you are going to draw a circle from the highest priority group to the lowest priority group that's facing you. This is going to be the second lowest priority overall. And that is going to determine whether this molecule is R or S. If the circle you drew is clockwise, then it's going to be R. If the circle you drew is counterclockwise, then it's going to be S. And for me, this is easy to remember because I just remember that if I want to turn right in a car, which way do I turn the steering wheel? I turn it clockwise, R. And I think this is another one of those things that you need to practice if you don't understand. Get a pen and paper out and just kind of help yourself understand this, understand how to do it. I wouldn't say it's super high yield, but definitely would not hurt to know the RS naming system. The other thing I wanted to talk about was the difference between absolute and relative configurations of stereoisomers. Essentially, the absolute configuration of a molecule is the precise arrangement of substituents at a stereocenter. So that is going to be the RS naming, where I could point at a stereocenter and you could say that's RS, and that doesn't change at all. However, for the relative configuration, we're looking at the position of atoms or groups in space in relation to another part of the molecule. So this is going to be the cis or the trans isomers, right? You're looking at the position of some substituent group in reference to another substituent group on the other side of the molecule. So you can think about relative configuration being cis-trans and absolute configuration being RS. The next thing I wanted to talk about was the relation of an SN2 reaction to stereoisomers. So an SN2 reaction is a nucleophilic substitution reaction, and it is a single-step reaction that results in an inversion of previous stereochemistry. So if you started off with an S molecule and that undergoes an SN2 reaction, you will now have an R molecule and vice versa. So if you start with an R, then you go to an S. So that's just something to keep in the back of your head as you're taking the MCAT. And before I go, I want to talk about one interesting case of stereoisomers in different sugars. And so obviously stereoisomers play a pretty big role in different sugars, right? As I was saying, glucose and galactose are 2 different diastereomers, whereas L-glucose and D-glucose are different enantiomers. The sugars I want to mention are allulose, sucralose, and glucose, which allulose and sucralose are two fairly common sugar substitutes. Allulose is a rare sugar that's found in nature, and they now invented this enzymatic process where they can create it in the lab. Sucralose, on the other hand, is completely lab created and is basically a chlorinated glucose. It has chlorine added on. So obviously, sucralose is not an isomer of glucose. It has a whole nother atom, and it kind of has a weird aftertaste. And I'm not sure if that's because of this extra chlorine group. I don't really know. On the other hand, allulose, which is also known as D-piscose, is a diastereomer of fructose, which this is very similar to sucrose, which is a table sugar, right? Sucrose is just a disaccharide of fructose and glucose. So this diastereomer of fructose, which is allulose, is actually very similar to this table sugar. And so allulose tastes a lot like table sugar. It has a very similar consistency to table sugar, but it is a different sugar, right? It's a diastereomer, and we don't have the enzymes to actually metabolize allulose, which is kind of crazy to me, right? We have enzymes to metabolize fructose, glucose, plenty of other sugars, but just this one sugar that's a diastereomer of fructose, we don't have the enzyme, and I don't know why. It's probably because it's pretty rare in nature, so we didn't ever need to have that enzyme, evolutionarily speaking. But anyway, so we can't metabolize the sugar, so it just passes through us, and we excrete it out, which, by the way, is pretty much the same thing that happens to sucralose, right? We don't have the enzymes to digest sucralose, so it just passes through us. So there's no caloric intake from these sugars, or at least very little intake of calories from these sugars. And very recently, in April of 2019, the FDA approved allulose to be taken off of the added sugar part of nutritional labels. So because of that, I'd assume that this substitute sweetener, or the sugar substitute, is going to get more and more popular, and we're going to start seeing it in more and more products. And that is it for the Isomers podcast. If you like this episode, please go give us a review on iTunes. It helps us in the rankings and helps us reach more people. And I always like seeing them as well. Thanks as always for listening. We'll see you next time.
Thanks for listening to Prospective Doctor's MCAT podcast. If you're a pre-med, you'll want to check out prospectivedoctor.com for tons of free tools, articles, and more podcasts that cover your pre-med life. And if you need help on the MCAT or getting into med school, check out medschoolcoach.com.